These notes are intended to help us understand different types of functions and how to graph them. So in all of the examples I'm going to give you, y is a function of x. The value of y depends on what value you plug in for x. So let's work through a few examples. Here's a rule that says y equals 2x plus 4. We can choose what numbers we want to plug in for x. There's no numbers that we're not allowed to plug in for x, because I can take any number and multiply it by 2 and add 4. So the domain for this function, the numbers I'm allowed to plug in, I can plug in anything I want. I'm going to plug in just a few particular numbers. I'm going to try an easy one first. I'm going to plug in 0 for x. So let me show the work of what happens when I plug in a 0 for x. I get 2 times 0, that's 2 times x, plus 4. 2 times 0 is 0, plus 4 is 4. And that's what y has to be, because y has to equal 2 times x plus 4. So when x is 0, y is 4. When x is 1, 2 times 1 plus 4, again that's 2x plus 4. 2 times 1 is 2, plus 4 is 6. When x is 2, 2 times 2 plus 4, 2 times 2 is 4, plus 4 is 8. You can tell that we could keep going with more and more positive numbers. We could plug in negative numbers for x if we wanted. We could plug in fractions. We could plug in just about anything we want. Let's show these points on a graph. So we have 0, 1, 2, 3, 4. That's our first point. We have 1, 1, 2, 3, 4, 5, 6. That's our second point. We have 2, 1, 2, 3, 4, 5, 6, 7, 8. And we could keep going forever and ever. You remember from our unit on linear equations that we can connect these points. And any point on this line is the solution to this equation. So all of the points that are shown on this line are solutions to this equation. So we need to describe this function in words. Well, one thing we might say is that we might say that y increases. The y value gets bigger as x increases. As x went from 0 to 1 to 2, x was getting bigger. Y went from 4 to 6 to 8, y was getting bigger. So that's one thing we might say. We might also say that this has a positive slope. We might say things like when x is 0, y is 4. You can imagine that we could describe this function in words a lot of different ways. Next, we'll work through another function. This is y equals negative 2x plus 4. So when x is 0, we have negative 2 times 0 plus 4. Negative 2 times 0 is 0, plus 4 is 4. When x is 1, we have negative 2 times positive 1 plus 4. Negative 2 times positive 1 is negative 2 plus 4. Negative 2 and positive 4 add up to 2. When x is 2, negative 2 times positive 2 plus 4. Negative 2 times positive 2 is negative 4 plus 4. Those add up to 0. And again, we can graph these points. 0, 1, 2, 3, 4 is there. 1, 1, 2 is the next point. 1, 2, 0 is right there. So in this case, if we wanted to describe this function in words, we might say something like this. As x increases, x went from 0 to 1 to 2. What happens to y? Well, y is going down. Y is decreasing. We might also say that this has a negative slope. And we could continue with our descriptions on and on. Now here's a different kind of a function. This is y equals x squared. Y equals x squared. Remember that x squared means x times itself. So let's plot some points here. When x is negative 2, what does y have to be? Well, negative 2 times negative 2. A negative times a negative is a positive, and 2 times 2 is 4. Negative 1, when x is negative 1, the function is negative 1 times negative 1. Again, a negative times a negative is a positive. 1 times 1 is 1. So when x is negative 1, y is positive 1. 0, that's a pretty easy one. 0 times 0 is 0. So that's a point there. Then if we plug in a 1 for x, 1 times 1 is 1. Now notice that we had two different inputs, negative 1 and positive 1, that gave us the same output. This is still a function because each input still has its own output that goes with it. When we plug in a 2 for x, 2 times 2 is 4. So if we were to plot these points, negative 2, comma 1, 2, 3, 4 is that point there. Negative 1, 1. 0. This looks kind of like a line, but not exactly. It's like it turned a little bit. Let's see what happens when we keep going. 1, 1, and 2, 4. Our graph has this sort of U-ish shape. So if we were to describe this graph, one of the first things that we might say is this is not a line. This is not a straight line. A word that we use to describe this function is non-linear. That means it's not a straight line. But that makes me think that another good way to describe our functions above here is to say that these functions are in fact linear. That the other functions that we graphed above do make straight lines. But not all functions make straight lines. In this case, we might say that as x gets further away from 0, and it doesn't matter whether we get further away from 0 by getting bigger or further away from 0 by getting smaller. As x gets further from 0, so as we move out on our graph, y is getting bigger. As x gets further from 0, y is getting bigger, no matter which direction we get further from 0. We'll learn later that the shape of this graph here is called a parabola. Parabolas have some very unique properties, not only in terms of math, but in terms of physics as well. Cool things happen when you make mirrors the shape of a parabola or speaker cones the shape of a parabola. They behave in some pretty cool ways. All right, so here's an example where I gave you some points and I want to know, can we fill in the graph from these points? In other words, if you have a function that's represented by a graph, can you work backwards to its table? Well, this first point here, this is 0, negative 3. I can tell because I go left and right, none, that's the 0, and then down 3. The next point is 1, negative 1. The next point is 2, and then positive 1. The next point is 1, 2, 3, and then positive 1, 2, 3. So I've made a table just by looking at that graph. I can tell that this is a relation again, where as x goes up, y goes up. I could say that it has a positive slope, and I could write a rule for it. The rule in this case is that y, the output I get, is negative 3, I got that from here, plus, as x goes up by 1, y goes up by 2. 2 over 1 is 2x. That's a rule that goes with this table and with with this graph. Next, I'm going to give you some descriptions about a particular linear function, and I'm going to ask you to sketch its graph. So the output, that is the y value, is 4 when the input is 0. That means that the point 0, 4 is on my linear function. Okay? So the output is 4 when the input is 0. 0, 4. 0, 1, 2, 3, 4. So that's 1 point. It says the output y increases as the input, that's x, goes from 0 to 5. So as I start at this point, as I move from 0 over on the x-axis, 1, 2, 3, 4, 5. So as I move to the right here, it says that the output, that's the y value, increases. It doesn't tell me how much it increases. So I can sketch in something like this. As the x-coordinates go from 0 to 1 to 2 to 3 to 4 over to 5. So this is a portion of the graph where as the x value increases, the y value also increases. Next, we have a separate section of our graph. This is a new section of the graph. And as the input goes from 0 to -5, so I'm starting here, and now I'm going from 0 to -5. So -1, -2, -3, -4, -5. I'm going to move backwards in the graph. The output doesn't change. The y value doesn't change. So my graph would look like that. So these are two separate linear segments. Then it says, challenge, in a different color, sketch a non-linear function. This means something that's not a straight line that meets those criteria. So all it needed to do was, my function needed to have a point here because the output is 4 when the input is 0. And it needs to go up as it goes from 0 to 5. So maybe instead of going up in a straight line, it goes up in a curve like that. And here, well, I can't exactly make the output not change in any way other than a straight line. So I can make this portion of the graph be nonlinear, but I can't really make this portion be nonlinear. Last but not least, we're going to sketch two functions. First, in red, we're going to sketch a function that meets these two criteria. The output, that's y, is 5 when the input, that's x, is 0. So 0, 5 is 1 point on our function. 0, 1, 2, 3, 4, 5. It's a point right there. And then each time the input, that's the x, goes up by 1, the output goes up by 2. So if we think about, we have this point, 0, 5. Each time the input goes up by 1, well, if the input goes up by 1, I'd go from 0 to 1. The output goes up by 2. I go from 5 to 7. So I can plot the point 1, 7 up here. So I might sketch the line through that in red. So there's a function that meets these criteria. Last, I want to do another function, and this one in blue. The output is 5 when the input is 0. So I still have the point 0, 5, because the output, y, is 5 when the input, x, is 0. So I still have that point there on my function. And here it says the output for the blue function, so that's the rate that the y is going up, increases twice as fast as it did for the red function. Well, in the red function, it went up by 2 every step. In my new function, I want that to go up twice as fast. So instead of going up by 2, I want to go up by 4. So when x goes from 0 to 1, y goes from 5 all the way up to 9. So that's this point here. So I can sketch my blue function there.